Thanks a lot, Alexei, for the introduction. It's really a great pleasure to be here and give this talk here on some recent experiments coming from actually University of Southampton and Skoltech in the Moscow region. But I'm from University of Warsaw, and I'm also a bit affiliated with University of Iceland. And just before I head into the material, I'd just like to acknowledge my main funding provider, National Science Center of Poland. And without further ado, I would like to introduce the wonderful team of people that has made all these experiments that I'm about to show you possible. So here we have the hybrid photonics group of Professor Pavlos Lagoudakis. He's here standing here in the middle smiling. This is taken on the Polaritonics Day back in 2019. And we have this wonderful collaboration with a lot of groups ranging from IBM in Zurich to, of course, University of Warsaw, University of Sheffield, and Würzburg, and many others. And it's really through the hard effort of these people that we have managed to produce a lot of exciting results in polaritonics, and mainly focused on Polariton condensation in planar cavities. So the content of this talk, the outline is quite straightforward. I want to give you a very brief introduction into optically trapped Polariton condensates that form the foundation of the results that I want to show you. And all of this work is really being pushed by this guy, Ivan Gnusov at Skoltech. So he is kind of the spear point in all this work that we've been doing. And the main results are in two parts. First, I want to talk about spinning up quantum vortices. So using non-invasive optical methods to stir up Polariton fluids to get vorticity. And then I want to switch into the vectorial or spinor picture and show how we can modulate polarization in these time-modulated pumping scenarios. And I want to give you a little bit of a flavor of something that we think is a non-equilibrium quantum fluidic analog of something that looks like the famous nuclear magnetic resonance effect. Okay, so we're all now very familiar with what are the polaritons, but I still want to show this slide mainly because now I have a new schematic here. It used to be a very old, boring schematic from my PhD thesis, but at University of Warsaw there's this person Mateusz Kroll, who is now gone to Elena's group in Australia, but he makes these really beautiful schematics, which we are able to use in our presentation and in our PR stuff. So, what is the exciton-polariton? So it is this hybridized mode between the cavity photon and the exciton. So we have the exciton level down here and the photon resonance in the cavity. That's one of the longitudinal modes in the cavity, which you can see by this yellow line here. And then the photons are absorbed and re-emitted by these electron-hole pairs, these excitons right here. And when you write your typical James-Cummings Hamiltonian or Tavis-Cummings Hamiltonian, you get these new eigenmodes, which are the exciton-polaritons. So we have the upper polariton branch and the lower polariton branch. And the light-matter interaction constant is defined by several properties of the material. And for the rest of this talk, I am going to be focusing exclusively here at the low momentum region at the bottom of the lower polariton branch, because this is where the condensation phenomenon is going to take place. Speaking of which, so what is this Polariton condensation? I have to give a little bit of an idea what it is, though I'm sure everybody knows now what it is. So back in 2006 and a little bit earlier, maybe a little bit even earlier than that, people discovered that there was an onset of macroscopic quantum coherence in these systems, something similar to lacing, but it was appearing in a strong light matter coupling regime where we had these polariton modes. So all people had to do, they could work at quite elevated temperatures, so 4 or 5 Kelvin, so liquid helium temperatures, and they could just ramp up the power of a non-resonant optical pump. And the process was thought to look something like this. So you excite a lot of electrons and holes, you create a plasma of electrons and holes, which then relax in energy through phonon scattering events. And eventually they form this so-called excitonic reservoir, which lies here in a bottleneck region where the dispersion starts to get a bit steep. And then if you add more and more particles into the system, at some point you will trigger bosonic stimulation and the ground state starts getting occupied, the average occupation number starts getting greater than 1, and this triggers more and more particle to go into the state, which becomes super coherent, and then we can measure all of the properties of this condensate by just looking at the photon modes which leak out of the cavity, which are of course coherent. So some people refer to this as Polariton lacing, other Polariton condensation, but the key thing is that this is an extremely non-linear fluid of polaritons, which is extremely coherent, and we can access it optically, which is very, very nice. It's not a lot of systems allow us to do this. So this is the schematic of typical cavity that we use. We use the Wolfgang Langbein generation of cavities, which have extremely low levels of spatial disorder. And we're dealing with vanadium excitons, so binding energies in several MeV, which means that everything has to be done cryogenically. The Q factors are in 10 to the power of 4, which is sort of typical for these planar cavities. And the beauty about these cavities is that because the low levels of disorder, we are able to optically generate structured fluids of polaritons with spatial coherence, which is almost unprecedented. So these things here, so these are not simulations, these are actual experimental images where we have detected the emission coming from Polariton condensates, where we have structured in this kind of a manner, square lattice, triangle lattice, honeycomb lattice, and they've all mutually synchronized and phase locked with one each other because there's a lot of coupling, in-plane coupling going on in these systems. And this is only possible if polaritons can travel from one condensate to the next and are not scattered away by disorder. So the low disorder is very crucial for these samples to show these beautiful patterns. So I will point out this nice work here by Julian Topfer that was published 2 years ago in Optica. Now, how do we create these structures? And this is also going to be relevant for the results that I'm going to show later, is that we use spatial light modulators that allow us to create all sorts of exotic pump profiles to excite polaritons with. So these are very versatile technologies that allow us to, at I would say, kilohertz rates, update the pump laser and create these various patterns of Polariton condensates, which we can play around with, manipulate, and explore all kinds of exotic geometries. So, and this is kind of a very basic schematic of our optical setup. And the nice thing about Polaritons is that you don't only get to optically write in a lot of information, but you also get to detect all the information by just doing optical measurement techniques. So you have access to near field, far field, spectrally resolved photoluminescence, temporally resolved photoluminescence, phase polarization, and et cetera, et cetera. So really nice systems to do measurements on. Now, this talk is going to be mostly about vorticity and a little bit about polarization. So I want to give here the basic introduction on how we define vorticity in these systems. So when we have a coherent object, a wave function, it can possess phase singularities where the phase is not going to be well defined, but it can possess a phase gradient that completes 2 pi revolution when you go around the singularity. So one way to look at it a little bit mathematically is that if you have your vector field, the flow of the particles, which is given by the gradient of the phase of this wave function, then if you encircle this phase singularity, then the curl is not going to be equal to 0, and it necessarily has to give you this quantization condition where the phase accumulation is going to be integer numbers of 2 pi. And because this is a quantized phenomena, we refer to these things as quantized vortices. Okay, but they're not exclusive to just quantum mechanics, to superfluids or BECs, but they also are quite fundamental solutions, even in the 2-dimensional harmonic oscillator, like Gaussian modes that we have there. And then, of course, there are optical vortices. And when we speak about Polariton vortices, I like to just stress that when we look at the emission, we are really looking at an optical vortex, right? Because the polariton decays into a photon, which then becomes just an electromagnetic field that contains this spiraling phase front. So when we detect these Polariton vortices, we're looking at optical vortices at the same time, which are, well, have become very, very popular to the growing advancements in phase singular optics. Okay, so now phase singular optics, you can also speak about Polariton singular optics or polarization singularities in Polariton fluids. It has led to a huge number of works focused on creating Polariton fluids with these phase singular textures. So we have everything from 2010. This is one of the original works from the Petran group, and we can go through all of this list. I just want to go very quickly through it. Notably, the very nice work here from Korea, which came in 2019, where they were able to show that you could inject orbital angular momentum to create Polariton fluids, even though the lasers were tuned far, far off resonantly of the Polariton mode. And then Alberto Amo was working on these hexagonal micropillar structures, where they were able to convert spin angular momentum to orbital. Sven and Sebastian, I don't know if Christian was on this work, but this is a work that was done in collaboration with Sukai Ma and Michael Schumacher. What's his first name? Sorry. Stefan. Sorry. I was going to say Michael Schumacher. So, yeah, that's a different guy. Where they showed non-resonant vortex steering, switching in structures. So huge plethora of works has been showing how we can explore vorticity in these Polariton fluids. Okay, so, and then there are these two works that came out nearly in parallel. One here from Jaakko and Michael Fraser in Tokyo, and one from Pavlos Davidakis group, where we showed that you could stir up vorticity in these Polariton fluids using non-resonant techniques, where all you would do is modulate the intensity profile of your laser and cause it to rotate around and exert some form of a torque on your Polariton fluid. So something, the analogy would be a little bit like stirring your coffee cup, but I don't know how good of an analogy that is, but you get the main picture here, right? Okay, so Michael has already given a really nice talk about the results for their work. So I'll be focusing, of course, on the results coming from Pavlos's group. And in order to make these results clear, I have to introduce a concept which is known as optical trapping of polaritons. So when we come in with our non-resonant lasers, we don't just create polaritons, we also photoexcite a lot of incoherent excitons in the background. And these excitons, where they accumulate, they will locally blue shift the polariton energies, right? So your optical beam does not only provide gain to the polaritons, but it also provides something like a potential landscape to them. So you can confine them, you can steer and guide them using your laser, just because it creates these exciton clouds which repel away polaritons. And so if you focus your laser on a sample in this kind of an annular pattern, then all you're really doing is creating something like a potential well that transversely confines the polariton modes. And then they can accumulate at the bottom of this well and form a coherent object. And this is exactly what was shown in 2013 by Jeremy Baumberg and Alexis Askitopoulos. So they took this kind of an annular laser profile, and they showed that as you increase the power above threshold, there was an abrupt transition. So this is more or less the profile of the laser, but then they saw this bright blob of polaritons appearing in the center of the laser, so quite far away from the actual maximum of the laser profile, but more in the minimum. So these were truly optically confined polaritons. And the nice thing about these polaritons is that because they are so detached from the actual maximum of the laser, the maximum of the exciton cloud, is that they show really extremely long coherence properties. So this is a preprint here on arXiv where Alexis showed that he could reach coherence times of these polaritons in the order of nanoseconds. So this is 3,000 picoseconds, 3 nanoseconds right here. And the typical lifetime of a polariton is only a few picoseconds. So we're talking about a 3 order of magnitude difference, which is just absolutely crazy when you think about it. So polaritons are decaying in a few picoseconds, but the coherence lasts for 3 nanoseconds. So these are very nice systems to look into long time dynamics, because the coherence lasts seemingly almost forever. And this is exactly what we wanted to do. We wanted to use these ultra-coherent condensates and see if we could play around with their time dynamics by modulating the pump profile So literally changing the intensity profile of the laser and try to stir up some some vortex solutions. So what Ivan did here is that he took two beams that passed through two different spatial light modulators. There were two different Gaussian modes, and then he combined them and he frequency detuned them a little bit. So what he ended up with was this pattern with broken axial symmetry. So this is going to be the optical pump that we use to excite polaritons, but it would rotate deterministically in one direction. And we were thinking, can we use this to stir up polariton vorticity? And so how it looks like, so if you take your two Gaussian modes, you superimpose them, you take the amplitude squared, you end up with a cosine squared, where you have some spatially varying phase profile and temporally varying phase profile. And this is how it looks like. This is how the profile should look like focused on the cavity. So this is just a little simulation, but this is what it should look like focused on the cavity. And the important thing is we go up to gigahertz frequencies, which is comparable to the timescales of the polaritons. Okay. So, and here are the results. So when we look at the emission coming out of the system, we see this very nice donut-shaped condensate forming. This is already very promising. It means that there is probably some sort of vorticity forming because there is this sharp density minima. And looking at the energy result emission, we see that there is practically only one mode condensing or lacing in the system corresponding to the first excited state manifold. And then we can do some interferometry and extract the phase profile and see the, well, it's maybe not very clear that there is a fork-like dislocation, but the phase profile shows a very nice singularity, which the phase rotates around in integer number of 2 pi, right? So this was pretty good evidence that our system was really exciting on polariton vortex. And then we, of course, do this little check, is the beam pattern actually rotating the vortex in a deterministic direction? So the rotation frequency of the pump, so if this is a positive number here, then it's rotating counterclockwise. If it's a negative number, it's rotating clockwise, if I got that right. So if you just change these parameters, either the detuning or the number of the angular index of your Gaussian modes, then you should be able to switch the vorticity in the system. And this is exactly what we see. So when we change the detuning from being positive to negative, we see a flip in the vortex because now the beam rotates in the other direction. And if you change the angular index, if you swap them, so you have +1, -1, and you go to -1, +1, then the beam starts rotating in the other direction, and you also swap the direction of the vortex. So this is so these are measurements that are highly reproducible. So this is not just a selected measurement, but we could actually reproduce this over and over and over again. And we looked into a little bit the statistics on what was happening in the system, and we found that there were sweet spots where these vortices could form. So if the beam is rotating too slow, so this is the rotation frequency, we don't see any vorticity. So this is kind of the distribution of vortices multiplied by their angular momentum. So that's why it goes to negative percentages and positive percentages. And this shape of the distribution tells indeed that the steering of the beam is steering the vortex. But if we go to very high rotation frequencies, the vorticity vanishes. And this is in stark contrast to what you would expect in normal superfluids, right? Because if you rotate your container faster and faster in a conservative superfluid, you should get more vortices. But this does not happen in our case. Well, firstly, because it's non-conservative system and it's driven strongly out of equilibrium. But why does the vorticity vanish when we go to high rotation frequencies? Okay, so here comes a little bit of theory. So I maybe should have made it clear from the beginning that I'm a theorist, I'm not an experimentalist. So I need to show at least that I'm doing a little bit of work. And the model we use to describe the system is this typical classical, like a nonlinear Schrödinger equation, but with a lot of non-Hermitian terms. So we often refer to it as a generalized Gauss-Krzyzewski equation. And what I want to just focus on right now is the solution to this bottom part here, this reservoir equation. So this last equation down here is what we refer to as a dark reservoir of high momentum excitons. And the solution is presented here. It's a little bit messy, but I also plotted it here in this panel. So instead of forming this, instead of following the pump pattern 100%, it is going to smear out a little bit, right? Because there is a decay term, the excitons have finite lifetime, so they don't respond infinitely fast to the changes in the optical excitation. There's going to be some tail lagging behind. And what this results in, it gives you this little bit of smearing, so you lose a little bit of the anisotropy in the trap that you're inducing for the polaritons. And if you spin it up faster and faster, it starts becoming more and more donut-like, and you completely lose your anisotropy, which means that you no longer have any distinction between clockwise and counterclockwise currents. And that is the reason why when you go to very high rotation frequencies, you just smear out your excitation pattern, and you lose all control over your vorticity in the system. Okay. So, and how can we model this? So, okay, when this is actually very similar to what Alexei Yulin was showing today, is that we can model this a little bit in the linear regime, which is very close to threshold. So we're gonna forget about that there are non-linearities and there's a condensate. We're just gonna look at the single particle modes very close to threshold and how they grow in time when you pass that threshold. So we'll write a single polariton Hamiltonian, and we're going to break up the Hamiltonian into two parts. One part is a cylindrically symmetric confining potential, which is the smeared out part of the pump. And then there's a perturbative potential, which is the anisotropic part of your pump. And so we'll just assume that it's going to be a harmonic confinement. So it doesn't really matter what sort of confinement you'll take in. This is just nice to work in because you have nice eigenstates to work with. And then this is our perturbation. I could have rewritten this as just a normal cosine, but I'm going to take it as cosine squared for now. Okay, so we have this part here, and we have this non-perturbed part right here. So what happens? We're going to take the solutions of the non-perturbed part, and we're going to use only the first excited manifold. So we're going to forget about the ground state, which is different from what Alexei was doing, but for now, just bear with me. And then we plug these solutions into our perturbed Hamiltonian, and we take the inner product over a real space, and we arrive at very simplistic equations describing the population and phase in the clockwise mode and the counterclockwise mode. And these equations you should be familiar with them. We see them all the time when we have a two-level quantum system and we are perturbing it with an oscillating electric field, right? These are the Rabi equations. The difference here is that we don't have a detuned two-level system. We have a two-level system where the two levels are at same energy. So this is an extremely non-resonant problem, like Alexei pointed out, right? So we have these two different frequencies which make the plus mode and the minus mode extremely non-resonant with each other. So they're very weakly coupled. Nonetheless, we can solve this model. We can write the general solution for it. So this is the general solution where I've redefined some new parameters, something omega r, which depends on the frequency detuning of our non-resonant laser and the angular momentum difference of these non-resonant laser. So, okay, all I want to just say is that we can solve it analytically. Now, here comes the trick. We're going to allow the perturbation, the lambda, we're going to allow it to be complex. It's going to be a non-Hermitian problem that we want to solve. And this has dramatic differences to the Hermitian case. So, and to see this difference, I'm going to define this measure, the measure of orbital angular momentum in a system. This is the general solution. And the more particles I have in the plus mode, the more positive angular momentum I have in the system. And the more I have in the minus mode, the more negative angular momentum I have in the system. So I can just look at how the angular momentum is evolving by solving this equation for different initial conditions. And if I take all the initial conditions possible, so the entire block sphere, and I average over them, I end up with this expression. So if the perturbation, the non-Hermitian perturbation, if I break it up in a real part, so this is coming from the real part of the potential, and this is coming from the gain region of the potential, we end up with something that is non-finite and actually diverging in time. This equation is just describing how the single particles acquire gain from the non-Hermitian perturbation, and they're going to grow exponentially in time until nonlinearities kick in. And the sign of this orbital angular momentum is dictated exactly like what Alexis said by the sign between the real part and the imaginary part and the rotation frequency of the beam. Okay, so if I change the rotation frequency of the beam from positive to negative, then the orbital angular momentum switches. Okay, so this expression makes a lot of sense because it fully describes the observed phenomenon when we look at just modes that condense first when you cross the condensation point. Right? So the orbital angular momentum is fully dictated by a few fundamental parameters of our model. And indeed, if we change the rotation frequency of the non-resonant laser, then we can flip the sign of this orbital angular momentum. So this is very nice because it's a very small and easy expression to get, and it's a little bit intuitive, and it shows how different the case is between the non-Hermitian and Hermitian case. Because if it's Hermitian, then this lambda j is 0, and this hyperbolic sinus is 0, and the whole thing just goes to 0. There is no net accumulation of orbital angular momentum because the Hermitian case doesn't distinguish between them. So you need this non-Hermitian factor to distinguish between them. Okay. And yeah, I just want to point out here that there is a much more detailed analysis done by Alexei and other co-authors, Ivan Shelik, Alexei Kawakin, on this matter. So I really want to point people out to check out this paper right here. Okay, so how much time do I have?
5 minutes.
5 minutes? Okay.
Something like this.
Something like this. Okay. I'll try to be quick. So I've been spending a little bit too much time gushing on about the theory. So now we're going to scale up the system. Okay. I said earlier that our system is very different from normal superfluids because we cannot spin up more and more vortices as we increase the rotation frequency. But we can do something else. We can increase the size of the trap. We can increase the size, and what this gives us, it gives us access to higher order angular momentum components, okay, or higher order modes in the system. So we can actually find here the second excited manifold and the third excited manifold by just changing the size of the trap and bringing more modes into resonance with the gain bandwidth of this condensate system. So this allows us to stir up one vortex, two vortices, three vortices, and we can go as high as we want. Well, maybe not as high as we want, because at some point the trap gets too big and you won't get condensation into it eventually. Okay, so there is a limit, but at least it was very nice that we could show that you can get these clusters of vortices. And notice they're all rotating in the same direction. So all these phase singularities have the same angular momentum, which follows the sign of the pound. Okay. And if you scan the power, if you crank up the power of the laser, you can lose vorticity. So here we have the first excited manifold where you have one vortex. Oops. And if you increase the power, then at some point you drop down to the ground state of the system and you lose your vorticity. So there's also a power control over the system. You can reduce the vorticity of the system by changing the power, which is again something a little bit different from what you would expect in superfluid systems. Actually, I don't even know what would be the analog of the power in a superfluid system. Maybe the density of superfluid particles. So now with the last 5 minutes, or a few minutes I have, I want to talk about polarization modulation. So this is really recent work that we came out with. So we know that polaritons, they have a spin structure. They have an integer spin structure ±1, which comes from the optical selection rules of creating excitons. So you have heavy holes, light holes, and you have the conduction band electrons, which can be excited by clockwise and counterclockwise polarized photons. So the spin structure of polaritons is explicitly related to the circular polarization of the photons that you get out of your cavity or send into your cavity. And this allows us to map the condensate onto the Poincare sphere, where here you would work with Stokes parameters corresponding to the different polarizations, but we can define a pseudospin, which is this macroscopic spin, which for all purposes here, analogous to the Stokes vector on the Poincare sphere here. So you have S1, S2, S3 as components of your pseudospin of this condensate, which is just the average projection of the spinor on the components of the Pauli matrices. And this gives you information how much of the condensate is going to be linearly polarized or circularly polarized. So you can just look at the photons, check their polarization, and you know what is the spin structure of your condensate. Okay, so Ivan asked the question, can we also engineer the polarization of the system? Because the trap that we create is anisotropic, which means that it should also break symmetry between polarizations along the major and the minor axis of this trap. And indeed, if we do shape the trap to be geometrically elliptical, we do find that there is going to be condensation into a mode which favors the minor axis of this trap. Okay, so the emission that we see from the condensate is completely polarized along the minor axis. And then if you change the orientation of this trap, the polarization follows in this sinusoidal way. So this is a demonstration of polarization tuning by only changing the geometry of your excitation pattern. And if you want to write it in terms of an effective magnetic field, it would look something like this. You would have an in-plane magnetic field with a cosine sinus term, which is just this transverse magnetic field, effective magnetic field, which is dictating the orientation of your pseudospin. And this was published 2 years ago in Physical Review Applied with Ivan here at the spear point. But then we said, let's apply our idea about the stirred up vortices, but now in a polarization picture. So again, he took two beams, frequency-detuned them, and he stirred up the trap. And first he started very slow. So we started with megahertz trap rotation speeds. And we saw using I don't remember the name of the equipment, but we could detect in real time the change in polarization because this is a relatively slow rotation speed. And we're able to sweep the entire equator of the Poincare sphere. Okay, so this is a very nice demonstration of polarization control at megahertz frequencies. But the really interesting stuff happens when we go up to gigahertz frequencies. Okay, so, and what is going to be happening is something that we call the self-induced Larmor precession. So we all know about the Larmor precession for normal electrons in a magnetic field. Polaritons, they also possess something analogous. When you pump them and you split their populations, because they are so interactive, they will create their own nonlinear magnetic field out of the plane of the cavity, and pseudospin will start precessing around this field, and it can precess at gigahertz rates, right? So we are able to reach really fast spin rotation by just splitting the populations of polaritons. There have been several works showing that this is possible, and the most recent ones came from Paulus's group here in both in 2022. And so I just want to give you this picture that you have a system that can have a stable orbital and the pseudospin rotates around persistently for a long, long time, many nanoseconds. And then we said, what happens if we create this Larmor precession, but we also spin up the trap? What happens if we change the orientation of the trap and we change the polarization ellipticity of our laser? So you have a magnetic field that now looks like this. You have a transverse part dictated by the orientation of the trap, and then you have an outer plane part, which is dictated by the ellipticity of the beam, the circular polarization of the beam. And we see a very sharp resonance in the G2. So the G2 is a measure of spin coherence or azimuthal coherence on the Poincare sphere. There is almost no decay in oscillations of the G2 when we look at the intensity correlations between horizontal and vertically polarized light, which means that there is some sort of a resonant effect happening, because everywhere around, when we tune the polarization of the beam, there is almost no G2 oscillations. And then suddenly we see this sharp jump. And what's happening is something very similar to a nuclear magnetic resonance effect. You have put your condensate in a position where it has some nonlinear field out of the plane, and then you come in with your pump, you spin it up, and at a very specific frequency, the pump is spinning, it resonates with the Larmor frequency out of the plane of the system, which is more or less what the nuclear magnetic resonance effect is about. And so if we extract the spin coherence time of the system, we got something that was almost reaching 200 nanoseconds, which is just unheard of in these Polariton systems. So really, you've created something like an ultra-stable orbital on the Poincare sphere, and your polarization follows in step with the rotation of the pump. Okay, and the corresponding Q factor would be in the order of many, many hundred, 546 to be exact. Okay, and of course we can model all of this using classical methods, so we see the same resonance when we just plug everything into a stochastic Rospilievsky equation, and so this doesn't require any quantum consideration. Everything can be modeled classically. And I want to point out again, Alexei is like one step ahead of everything. He already has a paper about spin resonances induced in these rotating traps. So again, yeah, you should check out this work here. And that is going to be my summary. Sorry if I went a little bit ahead of my time. I should. This is a new presentation. I'm sorry about that. So the summary is that we can stir up optical Polariton vortices. We can stir up the polarization of these systems. So we can do modulation of phase. We can do phase singular polaritonics through time periodic drives, and we can also do polarization modulation using these time periodic drives. And the future, the perspective of this is to maybe combine these ideas where you combine spin angular momentum and orbital angular momentum to create some hybrid phase polarization singular solutions in these systems. And an ideal platform for this would be liquid crystal microcavities, where you have perovskite layers and liquid crystals that are electrically tunable. And that will give you this electrical plus optical tunability for phase and polarization singularities in Polariton microlasers, which I think would be quite a fancy object to have in the future. And this is something that I'm hoping that the exciton-polariton group in Warsaw will pursue in collaboration with me. So here's the picture of the group. You have the team leaders, Barbara Pietka and Jacek Szyczko. And there are a few other faces in the group that are missing from this picture, but it's a wonderful group of people, and to be happy to see you if you ever come to Warsaw. And the final announcement of this talk is going to be a new conference series, which will start in Iceland. So I want to welcome you all to the International Conference on Physics of Excitons and Polaritons in Semiconductors. So it will take place next year in August. And you have the email here, the website address here, the QR code right here. And we will be hopefully sitting all together next year here at the University of Iceland. It has quite a nice campus that is very close to the city center. So hopefully it will be a good time. Hopefully the weather will play nice with us. And with that, I am going to end my talk. And thank you for your attention.
Let's finish speaking. And now we have some time for questions. Are there any? Yes.
Yeah, very, very nice talk. You showed the stochastic analysis of your the amount of angular momentum versus frequency.
Yeah.
Sorry, it's a question relating to the experiments. Anyway, I think I noticed some asymmetry from the left and from the clockwise to counterclockwise rotation directions.
Yeah.
So I'm wondering if you have so since you said the disorder was quite low, is there an alternate explanation for this, or do you think that this is just a material problem?
Yeah, I don't think this is a material problem. I think this is a beam problem. I think the beam is not exactly a perfect combination of two linear Gaussian modes. And I think this is the determining factor in any asymmetry in our system.
Okay, yeah, that makes sense. Yeah.
Helgi, thank you very much for your nice talk. I have a question. One of the slides you mentioned this G2 function. So can you please a little bit more elaborate on that? What do you try, which feature do you try to describe, and what is the method, how you calculate?
So how do I calculate it, or how do they measure it?
Is it only measurement, so that you don't have any theoretical results, it's just experiment?
No, we also have theoretical results. We also did the G2 because there's no, this G2, we don't think there's anything quantum happening. I know G2 is usually used as a measure of something quantum happening, but we used G2 here because we wanted to be able to see the intensity correlations between the two cross-linearly polarized signals, so the horizontal and vertically polarized signals. This gives us a measure of the, let's say, the kind of the azimuthal coherence on your Bloch sphere, but actually Poincare sphere. And it is more robust because you're looking at the intensity correlations. If you were to look at the G1, the coherence time would drop faster because then you have this additional phase, this dephasing in the G1. It's the overall phase.
Do you have the slope, how it drops down?
The G1 or the G2?
G2.
The G2, you know what? I might have it here as a supplementary slide. Let me see.
If it's too much of hassle, we can discuss it later.
Yeah, because there are like 60 supplementary slides on this. It drops exponentially. And we did this experiment last year on the self-induced Larmor precession, where we did this optical trap and we polarized the laser a bit. And we got almost an exponential fall off of the G2. And we extracted a coherence time from the envelope of the G2 in the order of 9 nanoseconds, which is why this is so interesting, this effect right here, because here we have almost 200 nanoseconds. So there's almost a 2 order of magnitude difference by using this time periodic drive technique here.
I think we have some time for the last question, and probably we can continue our discussion during coffee break. So I think it was first.
Just to avoid misunderstandings, this is TMTE splitting driving spin properties, or what is it?
TM splitting. Are you asking if that's a factor in our system that's causing this?
Yeah, I mean, the spin dynamics is driven by TMTE splitting, isn't it?
Yeah, so when we analyzed it first, so how does the polarization get pinned when you have this kind of anisotropic optical trap? One way to explain it is through TEM splitting, because TEM splitting, it correlates the spatial information with the spin information. So if you have anisotropy in your pump profile, it will affect the polarization. So TEM splitting is what we used to explain this in-plane magnetic field coming from the squeezing of this trap. But my opinion is that in order to get the actual strength of this in-plane field, you need to do some more fancy calculations because I'm not sure TEM splitting is the only thing contributing to this polarization pinning, because it's extremely weak in our sample. This sample that we're working on, we can almost not detect it. So it's a little bit difficult for me to imagine that TEM splitting is the dominant cause of this polarization pinning. So I think there is something else that we need to check to find out why the pinning is so strong in these squeeze traps.
Did you look at vorticity under polarization with soft measurements?
No, that's something we haven't looked into. So when I switched gears, I basically went from vorticity in scalar fluids to polarization in vectorial fluids, but everything is in the ground state. So there are no vortices here. Everything is just kind of homogeneously Gaussian.
Thank you.
Okay, then let's thank the speaker again and all the speakers of the section.